Let's take a look at a specific example here. We're going to be given a project network, and you'll see that on the next screen, but let's take a look at some of the cost data. And we're given some interesting information. We're given the cost duration graph, if you will, the normal and the crash points for these 7 activities. We're also given the slope, which represents the cost per day, and given the maximum number of days we can crash or reduce each particular activity. Those are shown in the first 2 columns of the table. This is an iterative process, and we'll start with the first project network and the normal direct cost and normal time for the project. Given the duration and information on the previous screen, and given this project network, we can see that the project will take 25 days and normally cost $450 to complete. We also can see in that first upper left-hand corner project network that the critical path is activity A, D, F, and G. That represents the full 25 days. So if we're going to go through and crash this project, we're going to look for the lowest cost activity on the critical path, reduce that one. That will give us a total project time reduction of 1 day, and we'll check and make sure no other critical paths have been affected, or no other paths have been affected and turned critical, and then we'll repeat until we hit a crash point. So what we see here in the upper left-hand corner, we circle activity A because when comparing the cost of A, D, and F and G, A is the cheapest one to crash. The cost is $20, and we can see the results of that in screen B in the lower right-hand corner. We've reduced A from 3 to 2 days, and as a result of that, the total duration for the project went from 25 days to 24 days, and we have not affected the critical path. One of the reasons we haven't done that is A is a burst activity, and so by reducing the duration of a burst activity, any other activity associated with that path, any other path associated with that activity will be reduced by 1 day as well. So the impact there is, if you add all the other durations up of all the other paths, they're less than 24 days. Okay, things get a little more particularly confusing probably at this point, but if you look at the top slide, A here, you can see that when compared to the last screen, we reduce D from 11 days to 10 days, reducing our time from 24 to 23 days. The cost of doing that was $25, as noted in the lower right-hand corner. The impact of doing this has effectively given us 2 critical paths, A, D, F, G, and A, C, F, G. So now we've got to change something along both those paths that will reduce the project duration from 23 to 22 days. In order to do that, and analyzing all the individual costs, you'll find that F is your best solution and your cheapest solution. So what you're seeing in the bottom part of this slide is the impact of moving F from 5 days to 4 days. The impact of reducing F by 1 day allows for the project to go to 22 days, but turns all paths into critical paths, as shown in this diagram. And so if we're going to try and reduce this to the crash point, we've got to figure out what else we can crash on every single path that will allow this to happen and do it the cheapest way possible. So our choices are going to be D, C, and E, or D, C, and B, and it turns out that D, C, E is the cheaper of the 2, and we'll see the results of that on the next slide. After reducing the duration of D, C, and E, the project total duration went down from 22 days to 21 days. All paths of the project are critical, and so since we can't crash G, because in the first slide it said G had no ability to be crashed, we are what's called the crash point for this, because one of our critical paths has all the activities at its least amount of time. So the path ACFG cannot be crashed anymore, and therefore we know we can't reduce this project any further. So let's summarize the results of what we did here. So we can put in the project duration for each day. We summarize the total direct costs, and what was given in this problem was an indirect cost of $50 per day. So for every day you did incur costs, you we're able to reduce it by $50. The indirect costs were set at $400 at 25 days, and so every day you don't work the project, you can reduce it by those $50. And what you'll find if you add the direct costs and the indirect costs together, you'll find that there's an optimum cost of $775 at 22 days. So you can reduce this project by 3 days, taking it from 25 days to 22 days, and actually save $75 in the process. We can see those same results in this project cost duration graph where we hit a local minimum or an optimization point at 22 days for this project. Some practical considerations when you're using these techniques to reduce project duration is first in using that project cost and duration graph. Those indirect costs are frequently forgotten in the field when pressure to get work done is intense. So make sure that you're taking a look and seeing where those optimum points are and understanding the impacts of what you're doing. Collecting information on crash times is tough. You've already set up an optimum way to do a particular activity, and now you're bringing in additional resources, whether they be equipment or people, and so understanding the total impact of what you're doing there sometimes becomes a bit of a challenge. Well, it's all fun and good if we've got the resources available to reduce projects by throwing additional essentially money at it, but what if cost, not time, is the issue? What do we do then? Well, there are other things we can do to get the project done early. We can reduce the project scope, have the customer agree to some reductions along the way that will essentially save us time, and then the impact, won't have any impact in terms of cost. Maybe we give the project owner more responsibility, have them take on part of the project, and then that reduces our costs and also speeds up the project. Perhaps there's an opportunity to do some outsourcing. And maybe if all else fails, bring the project team back together and have a one-on-one session with them all and brainstorm away and see if you can find some other ways where we can squeeze a little bit more money out of the project. This concludes the Chapter 9 asynchronous lecture. I posted some videos and worksheets for you to practice the crashing process, and by all means check those out in our asynchronous session this week. Beyond that, you have SEEs that are due next week for Chapter 7, and so please start working on those as well. We'll see you next time.